calculus students, flange here, and we've got quite a lot to cover today, but it's a lot of review. And plus, you'll see some of the topics on here in both P3 and P4 talk about model and real life problems. And we're going to be looking at those in some of the homework problems that the examples they do in class. So for right now, let's get started with plotting points in the coordinate plane. You're all familiar with the XY coordinate plane. And we always put the X coordinate first, and then the Y coordinate, 2, 1. Great. And these are the quadrants 1, 2, 3, 4. In terms of determining how quickly to talk about what quadrant we're in. Now, find the distance between 2 points with the distance formula. Notice they talk about the distance formula here. Let's just circle this with the distance formula. Where does it come from? You know, if I ask the distance between distance from 1, 2 to 4, I don't know, 6, we could actually use graph paper. I encourage you occasionally to get out your graph paper, and I've got that right over here. Hang on, just slide this out here for a second. Let's pause. Kids, I found some graph paper. So here we're going from 1, 2 to 4, 6. 1, 2, 3, 4. 2, 3, 4, 5, 6. There's our X and Y axes. And so you could just say, hey, we want this distance between these 2 points. Let's just look at the triangle. We're going over 3 and up 4. I think a lot of you remember this from geometry. That's right. The other side is 5. So our distance is 5. So that worked out to be a nice 3/4 triangle. And to do that, just to illustrate that we've got the distance formula, which looks like this. Square root of x1 minus x2 squared plus y1 minus y2 squared. Okay? x1 minus x2 squared plus y1 minus y2 squared. Now, let's see if it works in the distance formula. We take the square root of, at our 2 points, 1, 2, so 1, and 2 was the first y coordinate. And now from the other point, which was 4, 6, 4, 6, we can see how this works. You get the square root of negative 3 squared plus negative 4 squared. Square root of 9 and 16, square root of 25, and sure enough you get 5. Okay, that's the distance formula. And you see how it really is an extension of the Pythagorean theorem. Now the midpoint formula, setting between 2 points, is merely the average of those 2 points. The average of each coordinate. So you got x1, y1. Over here you got x2, y2. So the midpoint, the point in between there, is going to be the average of the x's and the average of the y's. And you can do this with a little geometric proof as well. If somebody wants to submit that, just a little diagram of how that works, kind of like with the distance formula, that'd be my guess. Now we actually get into some graphing. Sketching graphs of an equation is a whole category of things you want to look for. But today I'm going to mention some of the first things you should look for in a sketch. So some of the things you should look for in a sketch. First, the x and y intercepts. And these are pretty straightforward to find. The x-intercepts, doesn't matter what kind of equation it is, if you got the equation, you can find the x-intercepts by setting y equal to 0. Conversely, y-intercepts by setting x equal to 0. Okay? And you do this a lot with lines right away. As you recall, if you have a 5x minus 3y equals 30, we can make your little chart, XY chart. And if you set x equal to 0, imagine if I were to put a box, over this. Boom. And all that was gone. Okay? Then you'd just be left with negative 3y equals 30, so you'd get y equals negative 10. Negative 10. Conversely, if we set y equal to 0, now you cover up all this, you get 5x equals 30, so x equals 6. And actually you recognize this form as a line, so there's one quick sketch for you. 0, negative 10, and 6, 0, boom, 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 boom. You got it. Okay. Now use symmetry to sketch the graph in equations. A lot of graphs have symmetry. And first you can understand the idea of even symmetry by looking at the alphabet. Even symmetry is sometimes referred to as vertical symmetry. And for this, I'm going to break out some perfect letters here and give you a nice list, nice big list of some nice even symmetry letters. Make that a tad bigger. And now I can show you how each of these letters has even symmetry, because we can take a vertical line, and go right down the center of it. See the symmetry? There are mirror images over that line. There you go. You're getting better, Mr. Lane. Oh, that's hideous. I'll fix that later. All these have vertical symmetry. Okay, excuse me while I get these fixed. Okay, do you see the vertical symmetry in each of these letters? We look for the same thing in graphs. We call it even symmetry in graphs. If f of negative x equals f of x. This is a way you can tell that a function has even symmetry. And graph-wise, that's the functional notation. In terms of the picture, it will be f will be symmetric over the y-axis. Over the y-axis. So let's look at some examples of functions that do that. Some functions that do that would be y equals x squared. Basically your very basic happy parabola like this. It has symmetry over the y-axis. Y equals the cosine of x. You remember studying that from before? A lot of times you just go mom like this. But remember, you'd also go in this direction too. And again, you see symmetry over the y-axis. How about y equals x to the fourth minus x squared? Well, I don't know what that looks like. It's a fourth degree polynomial. It has roots at 0 and I think 1 and negative 1. And when you look at the graph, you get something like this. You might say, well, that's great, Mr. Lang. You know how to graph all those odd things and everything like that, but we don't even know how to graph those yet. We haven't reviewed them. Well, we'll review it. And for right now, you can do the symmetry test by test for even symmetry with negative x comma y. And if negative x comma y gives you the same equation, then you're all set. We start off with y equals x to the fourth minus x squared. Right? X to the fourth minus x squared. Now, we put in the point negative x comma y. So it becomes y equals negative x quantity to the fourth minus negative x quantity squared. So you get y equals x to the fourth minus x squared. And it's the same thing. These match. So therefore we have even symmetry. So you have here both the visual test up here. If you know how to graph, you can test for symmetry that way. But if you don't know the graph yet, you can use this algebraic test to see if it has even symmetry. I wrote some letters that have odd symmetry. Why these letters have odd symmetry is this. Here we go. Because we can take the letter and put a dot right in the middle and rotate it 180 degrees. Maybe I should make it 180 degrees, a little better. 180 degrees. And you still up with the same letter. You don't want to rotate 360 because anything rotate 360 will be back to itself. But if you rotate this 180 degrees, you're back to the same letter again. That's odd symmetry. You can also think of it as a double flip over the two axes. So Z, we can go right here, rotate 180 degrees. Same thing with O, there's the center of the point symmetry there. X, N, and H. Imagine rotating all those 180 degrees and you're back to themselves. So I call those the odd letters. Now you can think of the same thing with functions. This looks like this. So if you rotate it around the center 180 degrees, you'll be back to itself. Y equals the sine of x. A lot of times you just graph the first cycle like this, but as you go off in the other direction, you come back around like this again. Notice if you rotate that 180 degrees, it's back on itself. So those are some odd functions. And the test, so y equals x cubed minus x. This ends up being odd because if we put in negative x comma negative y. So we put negative y in for y, we put negative x in for x. And negative y equals negative x cubed plus x. We multiply through by negative 1, you get y equals x cubed minus x, which is what we originally started with. Okay? And to verify this, I want to show you a quick graph. So here comes the graph. And here's y equals x cubed minus x as a graph. And you can see that right in the center here is our point of symmetry. And if you rotate it 180 degrees, it will come back onto itself. So that's a visual illustration of why this has a symmetry over the x-axis, over the origin. Now another thought on this too is you can test symmetry this way. Is f of negative x equal to negative f of x? That's the question to see if something has odd symmetry. So in this case, we can also look at this function as f of x equals x cubed minus x. F of negative x equals negative x quantity cubed minus x. So you have f of negative x equals negative x cubed plus x, which is the opposite of x cubed minus x, which is the opposite of f of x. Just another notational way to study if something has odd symmetry or not. Okay.